let us pass to the next talk of Ed Potter from APS Paris. Okay, please do. Okay, so he will talk about fundamental physics and cosmology after the second LIGO-Virgo gravitational wave catalog.
And start the video. Okay, thank you very much for your patience and for inviting me to give this presentation. So I'm basically going to talk about what's going on with physics and cosmology after the second transient gravitational wave catalog from the LIGO-Virgo collaboration. So this is denoted O3A, and this basically covers the period of April 1st until October 1st, 2019. We basically aimed for around 10% contamination of the sources, so that roughly less than 10% could be produced by noise. This accounted for a false alarm rate of about 2 per year. At the end of O3A, we had 26 public alerts that had gone to the astrophysical community, and there were 13 events that were announced for the first time. So this basically gave us 39 events and 11 from previous catalogs. So we now have around 50 gravitational wave candidates. If I now go to the performance for the detectors in O3A, we can see that Virgo was, I'm assuming that everybody can see my mouse as I'm pointing.
Yes, we can see it.
Very good. So Virgo was basically operating at just over 40 megaparsecs for the median binary neutron star range. LIGO Hanford was operating between 100 and 120, and LIGO Livingston was basically operating somewhere between 120 and 140. On the right-hand side, you can see the median binary neutron star ranges for the 3 detectors. So just a quick kind of prelim on how we actually search for gravitational wave sources. We use a technique called match filtering, which is the optimal linear filter for a signal buried in Gaussian noise. This is very, very much phase dependent rather than amplitude dependent, so it requires very accurate theoretical waveforms with extremely high precision in the phase evolution. To basically make sure that everything is consistent, we use 2 different waveform families. We have a time domain waveform family, which is based on solving Hamiltonian evolution, and we have an analytic Fourier domain waveform that we basically use as well. Both of these waveforms are calibrated with results from numerical relativity for extra accuracy. We also have a number of unmodeled search techniques, which usually used different types of filters for searching for signals. The advantage of these particular search methods is that they don't have the a priori assumption that the waveform has a certain morphology, and they can be used to find unknown waveform types in the data. To extract the science and to extract the parameters, we use a full Bayesian inference package. So this is going to be my only data analysis related slide, but it's just to show kind of what match filtering actually does. So in the top panel, I'm plotting the signal to noise ratio time series. In the bottom panel, the blue here is the data. And then I've got 2 templates. I've got the green template and I've got the orange template. We can basically see that as we're passing the green template through the data, it's not phase matching the data very well. And you can basically see up here in the top panel that we're getting some bumps in the signal to noise ratio. And this is usually when you have 2 peaks coincide in the data. But in general, the signal to noise ratio is quite low. When we evolve the parameters of the waveforms such that they basically give a best fit match to the data, we can see a spike in the signal to noise ratio. So this is essentially how match filtering works. Now, the important thing about match filtering, and one of the reasons we can use it to test modified theories of gravity, is that you don't actually need to make very, very large differences in the phase. So for example, we know that if you include spins which come at the 1.5 and 2.5 post-Newtonian order, or if you include tides, which come at the 5 and 6 post-Newtonian order, they can be sufficient to dephase the waveform enough that you're not matching the data properly. And basically, we're going to use this concept when we run our tests for general relativity. So this is the current situation of detected events after the second gravitational wave catalog. We can see that we're basically building a zoo of black hole sources, some of them which are basically producing black holes on the order of 160 solar masses, which currently is presenting a difficulty for parents to build a supernova, because the precursors of this event, which are up here in the 60 to 85 solar mass range, shouldn't really exist according to the standard astrophysical stellar evolution. We can also see that we have potential neutron star black hole systems, and we also have potential neutron star systems. I say potential because our gravitational waveforms assume a point particle approach. And because of the fact that for some of these events, there's no electromagnetic counterpart, we basically can't actually say if these low mass events are extremely light black holes, extremely heavily neutron stars, or even down here, we can't rule out for definite that they're not primordial black holes. But we're working under the assumption at present that these low mass objects are neutron stars. This is basically the result in terms of the mass ratio and total mass for the events that we're actually detecting in O3. And we can basically see we have, things that are binary neutron stars, potential neutron star black holes, but the vast majority of what we're seeing is up here in the black hole section. In terms of the spin measurements, we can see that the effective spin for many cases doesn't actually rule out spin equals 0. We do have one event which basically does have an extremely high spin. And this is probably the clearest event so far of higher spinning systems. So let me move on to what we actually do for testing general relativity. So not all of the sources that we detect are viable sources for these particular tests. The higher the mass of the system, then the lower in frequency that it's merging. What we want to do in a lot of cases is we want to make sure that there's a consistency between the well-developed analytical foundations of the early in spiral and the merger ringdowns, which are coming from numerical relativity simulations and black hole perturbation theory. So in order to do this, we basically require the signal to have a signal to noise ratio of at least 6 in the in spiral and at least 6 in the merger ringdown. So this basically rules out a number of events, and for a lot of the tests in the system, we use 24 out of the 39 events used. So I should highlight some caveats here. We are not testing alternative theories of gravity. We don't have the mathematical foundations or the waveforms to do specific tests for specific theories of gravity. So our goal is to check the consistency of general relativity predictions. One of the things that we can do is we can add parameterized modifications to the gravitational waveforms using general relativity as the foundation, but then assuming that there's some perturbations on the general relativity waveform and look to basically constrain those perturbations. Because of that, our results should basically be interpreted more as observational constraints on deviations from general relativity rather than observational constraints on modified theories of gravity. Currently, the vast majority of our constraints are dominated by statistical uncertainties coming from detector noise. As the detectors improve, or as we move to third generation detectors such as Einstein telescope, these statistical uncertainties will basically diminish and we'll be able to make more accurate predictions. And in all our cases, we assume quasi-circular orbits, so there's no eccentricity. If there is an eccentricity, it obviously changes the phase of the waveform and has an effect on the predictions that we're making for deviations from general relativity. So we have 4 main tests. The first one is to look for residual power after we remove our best fit gravitation or general relativity waveform. So we do the search, we do the Bayesian inference, we basically come up with the GR-based waveform that gives the maximum likelihood. We basically subtract that, and then we want to go back into the data with various techniques and make sure that what's left behind is consistent with noise. We also have what's called an IMR analysis, where we compare information coming from the pure and spiral with information coming from the merger ring down and make sure that there's a consistency in the predictions of things like total final mass, final spin, etc. We then have parameterized tests of gravitational wave generation and propagation. So I'm basically going to tackle each of these in turn. So the residual power test, as I said, you subtract the maximum likelihood gravitational wave, or sorry, general relativity waveform, and then we use one of our unmodeled searches to go back into the data and place a 90% credible interval on the coherent signal to noise ratio that's left behind. We can also try and go back in with a template and basically see if we're getting phase consistency between a template and what's left in the data. But if general relativity is a good fit to the data we're getting, then there should be virtually no residual pattern left behind. And if what is left behind is consistent with instrumental noise, then the p-value for this should be uniformly distributed between 0 and 1. So in the top right here, I'm basically plotting the residual signal to noise ratio at the 90% credible interval and the signal to noise ratio from the general relativity waveform. Because the signal to noise ratio is essentially proportional to the amplitude, if there's a dependence between what's left behind and the original amplitude of the waveform, there should be a specific pattern in this plot here. Because of the randomness that we're seeing, we're basically seeing residual SNRs that are based on the performance of the detector at a particular time rather than on the signal itself. So this test basically says that what's left behind is consistent with instrumental noise. We then do the p-value test by looking at a number of off-section parts of the data where we know there's noise only. And the light blue band here is the 90% credible interval. If the null hypothesis is correct, so the null hypothesis is that we've pretty much removed all of the signal and everything that's left behind is consistent with instrumental noise, it should lie along this dashed line. And we can basically see what our measurement here is in the dark blue line, which fits well within the 90% credible intervals and is very much consistent with the null hypothesis. So the residual power tests basically tells us that, at least in this case, the signals that we've removed using a general relativity-based template has basically fitted the data to the extent that anything left behind is consistent with instrumental noise. We can also use the in-spiral merger ring down test. So we basically cut the waveform at the m=2 gravitational wave frequency at the innermost stable orbit for a Kerr black hole. We again require at least a signal to noise ratio of 6 in the in-spiral and in the merger ring down parts. And then we define these two dimensionless parameters here. If general relativity is correct, then these two parameters should be identically 0. What I'm plotting over here is the 90% contours for all of the sources that were used for the test. And in the vast majority of cases, they're basically incorporating the 0, 0 point, which makes them consistent with general relativity. This particular system here is not incorporating the 0 point, but we know that this system also demonstrates higher multiple modes in the waveform. So it's failing this test more on a technicality than anything else. What's important in this particular image here are these two gray distributions, which is the combined posterior distributions, combining all of the detections together. And we can basically see that the general relativity value of 0 is confined within the 90% credible intervals. So the IMR test basically gives us no reason at this point to doubt general relativity either. The next thing we can do is add phase modifications to the waveform. So as I said, we have two different waveform models. We can directly constrain the phase coefficients in two different ways. One of the things that we know is that a specific alternative theory of gravity will affect the gravitational wave phase dominantly at a particular post-Newtonian order. So basically what we can do is we define the phase coefficients. So here we have the in-spiral, the intermediate part, which is kind of merger and beginning of the ring down, because we don't exactly know where the merger and ring down begins and ends. And the pure kind of post-in-spiral part of the waveform. And then what we can do is we can perturb these coefficients in this form here and basically treat this delta pi as a free parameter. So we then go back into the data, and for every single phase coefficient, we run a test whereby we keep all of the other coefficients at the general relativity value, and then we perturb one of the coefficients at a particular post-Newtonian order and basically see if we can measure a deviation from the general relativity predicted coefficients. So I like to show this because it shows basically where we've come since 2016. So if I look at the upper bounds, just on deviations on the post-Newtonian coefficients in the in-spiral part of the waveform, after the first detection, this was the upper bound for the post-Newtonian coefficients up to 3.5 post-Newtonian order, excuse me. And here I'm plotting the restriction on the Newtonian order coefficient coming from, from this particular pulsar. I basically highlight as well that this constraint here is based on 10 years of observational data, whereas this constraint is based on 200 milliseconds of observational data. So then after the first gravitational wave catalog, we're mostly concerned with the gray and the open black diamonds. We can basically see that if we squeeze this part of the parameter space into this image here, that we have an improvement on all post-Newtonian coefficients given the extra detections. And then we come to the comparison between the first and second catalogs. And in pretty much all cases, we have an improvement on a factor of almost 2 in the in-spiral coefficients and about 1.5 in the post-in-spiral coefficients. One of the nice things to see is that we can essentially constrain potential dipole radiation at the -1 PN order to the level now of about 10 to the -3 deviation from 0. So then the next thing we can do is, while it's good to have the upper limits, it's also good to have the posterior distributions and the 90% credible intervals. So again, this was based on the very, very first detection, and we're mostly interested in the red forms. So each of the red forms here is a posterior distribution. The 2 lines denote the 90% credible interval. So this is where we were with just one detection, and we can see that not every single one of the deviations was incorporating the 0, which is the prediction from general relativity. Once we had the first catalog, once we had the first catalog, we can see that we did start to do a lot better. And there's still some distributions or some parameters where the general relativity prediction is just barely making it inside the 90% credible interval. If we now come to the results after the second catalog, we can see that pretty much everything is pretty much centered on the general relativity prediction. And one of the things that I'd like to bring to your attention are the scales. So at the end of the first catalog, these particular parameters here were kind of scaled between -6 and 6. They're down to about -3 to 3, which again is the factor of 2 improvement. And again, we've basically almost kind of halved the error bounds in these parameters as well. So from these phase modifications, again, we're seeing absolutely no reason to doubt general relativity. We're seeing no strong evidence for deviations from relativity at all. So the next thing we can do is we can basically do a dispersion test. So in general relativity, this alpha parameter here would be 0, and we would just be left with a dispersion relationship of this form. One of the nice things about this kind of relationship is that it puts a direct change into the phase of the waveform. And again, while we're not testing particular theories, we can make a relation between different theories of gravity dependent on the values of alpha. One of the ones that we're most interested in is a measurement of the mass of the graviton, which corresponds to alpha equals 0. So these great triangles were basically the results at the end of the first catalog. One of the things that I want to bring to your attention is the scale here. We're basically looking at an amplitude on the order of 10 to the minus 19 pico-electron volts squared. So this is the type of deviation that we're measuring at the moment. The blue diamonds here are now the improvement that we have from the second catalog. And you can see that we have roughly a factor of 2 in most cases improvement. This has basically allowed us to measure or to constrain the mass of the graviton to this particular value here, which is at the moment approximately twice as good as the best solar system bound for the mass of the graviton. One of the final things that we can do is we can basically test for excess polarizations in the waveform. So we know that in general relativity, we just have 2, but in generic metric theories, we can have up to the 6 polarization. Now that we have 3 detectors working pretty much all the time, we have enough degeneracy to break the, now that we have detectors working all the time, we have enough detectors to break degeneracy in the polarizations. We still don't have enough detectors to make individual measurements of the various polarizations yet. But one of the nice things about this test is that while you can use gravitational waveforms to test for polarizations, the important thing is essentially the geometric projection of the gravitational wave signal onto the detector. So every single one of the detectors will have an antenna response function. We can basically see how the detectors respond for the plus and the cross polarizations, the 2 vectorial polarizations, and the scalar polarization. One of the things that we can see here immediately is, mostly highlighted here, is that because of the antenna response function, there are dead spots in the sky. So if a gravitational wave is coming in along this axis here, it basically will correspond to a null point in the response function, and we essentially don't see it. Whereas a gravitational wave coming in from the top, we will basically detect it with maximal signal-to-noise ratio. And you can see how then the response function changes for different types of signals. So at the end of the first catalog, we weren't able to do, well, we still aren't able to do mixed polarization tests. The test we were able to do is imagine the gravitational wave is purely tensorial or purely vectorial, or purely tensorial or purely scalar, and basically see if there's a preference. And basically what we found at the end of the first catalog was that the data prefers tensor to vector by a factor of 200 to 1 and tensor to scalar by a factor of 1,000 to 1. So this time around, instead of using templates, we have a new null stream test. So rather than using any gravitational wave templates, we're just using the data that's coming from the detectors. In this particular case, I'm plotting kind of log to the base 10 of base factors along this axis. Anything below the 0, anything strongly below the 0 would basically hint that we should prefer vector or scalar polarizations above tensorial. We can basically see that in pretty much all cases for all the different tests, we definitely prefer tensor over scalar. The vectorial is a little bit more difficult to measure because of the types of signals that we're currently detecting and because of their strength. We again can't kind of definitively say that we absolutely prefer tensorial over vectorial. But in terms of the relative scaling, if I go back to this one here, there's a factor of 5 difference between how much we prefer tensors over vectors and tensors over scalars. And we're seeing pretty much the same thing here. So the question is, should we be surprised? And the answer is not really, because our fundamental kind of assumption when we're doing the analysis is that general relativity is correct. All of our waveform templates are based on general relativity. We basically do a number of tests like the residual test where we extract what we think is the signal from the data, go back in and check it. And in most cases, we're basically finding that the data is tensorial on the 96% or greater level. So it is possible that nature may be a mixture of tensor, vector, scalar, but if it is, then the vector scalar part really is the kind of the very, very small component, and it's vastly coming from the tensor components. So I'm almost out of time. A couple of the other tests that we've done that I don't have time to go into is we have done a search for gravitational wave echoes after the second catalog, and we find no evidence for gravitational wave echoes. We made no detection of cosmic strings. We, this time around, have a specific kink search, and we've basically detected nothing. It's allowed us to put a stronger bound on G mu than we have been able to before, but we're not seeing any evidence of gravitational waves from cosmic strings. And while we had a couple of tantalizing systems, we again have found no evidence of lensing in any of the current events. So with that, I will conclude. So O3A gave us 39 new candidates. We have no electromagnetic counterparts, which does make some tests of general relativity quite difficult. One of the crowning achievements of the discovery of GW 170817, the binary neutron star, was that with the detection of gamma rays, we were able to constrain the speed of gravitational waves to be almost that, well, to be essentially that of photons. In this case, we've had no electromagnetic counterparts, so we haven't been able to put any more stringent constraints on any of those tests. However, the multiple tests that we've done investigate different sectors of the gravitational wave. So we do essentially a weak field, mid field, and strong field range of tests. And at present, we have found no deviations from general relativity whatsoever. And with that, I'll finish. Thank you again for your patience.
Okay, thank you. Thank you for the interesting presentation. Please, questions. Alexander Zakharov.
Okay, do you hear me?
Yes.
Could I ask a question?
Yes, please. Of course.
It's the speaker said that, as Ed said, that in principle, if you have black hole coalescence, in this case, it's very hard or impossible to detect electromagnetic counterpart. Of course, it's natural if there is no matter around the black holes. But if these supermassive black holes were formed as a result of stellar evolution, it has to be very strong stellar wind. It means it is a matter there. If there is a matter, in principle, so it was a, let us say, like shock for this matter due to gravitational waves. In this case, it's LIGO people were very smart and they tried to find counterpart for the first events. But if you consider heavier and heavier black holes, this effect may be even stronger.
Yes, that's a very, very good point. I should have clarified that all of the results I'm presenting here are based on stellar mass black holes, where we assume that it's a completely clean system. I agree that in the case of supermassive black holes, it is possible that there's a circumblack hole or a circumbinary disk, which is basically taking part in parts of the inspiral, which will give you an electromagnetic counterpart. But in these particular cases, I'm like, we're currently limited to a total mass of approximately 500 solar masses for ground-based detectors. And there has been propositions that maybe some of our events are happening in disks around AGNs, in which case we might have an electromagnetic counterpart. But for the vast majority of the sources that we're seeing, we're assuming that these are essentially isolated field binaries with no material content, except for the case where we potentially have a neutron star in the system. In that case, we might have an accretion disk left over from stellar evolution, but again, it's not clear.
Sorry, is it okay? Because I don't hear anything. What happened? Evgeny, please do.
Yes, thank you. Hi, Ed. So I have a question about cosmic strings. So you said there was no indication of cosmic strings. So I would like to ask you if it's did you for sure you probably expected some tension, some specific tension, or is there some just a constraint on the tension? Because if the tension is very small, then you are not supposed to see anything. Or can you?
I didn't put the number here, but there is a constraint on G mu.
All right.
And you know, as you know, I'm like the problem with trying to detect cosmic strings is that most of the radiation is beamed. And unless we're looking right down the beam, they're very, very difficult to detect. I can't actually share my screen, but if you follow the archive link, they do look at about 4 different models, and they do give constraints on G mu for each of the 4 models.
Okay, thank you.
Okay, Takahira, please go ahead, Takahira.
Yeah. So I want to ask about this vector or scalar polarization. And when you discuss the possibility of purely vector or scalar polarization with the same GR waveform, do you have some model in mind? Can you hear my question?
So yeah. The most recent test is we don't actually use any waveforms whatsoever.
Yeah.
Because what's most important is how the signal is geometrically projected onto the interferometer. You can basically use null streams, which means that you don't have to make any assumptions on your waveform. The downside of that is that then you don't get a strong constraint as if you use waveforms. But if I remember rightly, because it's amplitude dominated, it doesn't actually really matter for the polarizations what the phase evolution is.
Yeah. So you mean that without assuming the waveform, you analyze the data, just taking the correlation between the different detectors?
Yes.
I see. So it's something like a background radiation search.
Yes, exactly.
I see. I understand.
Okay, is it good? Okay, then next question is Jie Chen, please.
Yes, thank you for the nice talk. It's just a quick question. Maybe you have mentioned, but I missed it. So in the method of residual power, do you consider the whole waveform template, which includes the spiral merger ring down part, or just part of it? For
the residual test?
Yes.
Basically, it's a 1 second window around the trigger time. So we expect that that's where the majority of the power is going to come from. But to remove, sorry, to remove the signal, it obviously depends on the type of signal. If it's a binary black hole, then we use in spiral merger ring down waveforms. If it's a binary neutron star, we essentially just use the in spiral part, because at a certain frequency, the data isn't properly calibrated. So it makes no sense to include the merger ring down parts.
Oh, okay. I see. Thank you.
Okay, good. Next is Cedric. Hi, Cedric. What's your question?
Yeah, hi, sorry. In fact, I had the same question as Takahiro, so you can skip my question, sorry. Thanks very much for the talk, by the way.
Hi.
Ed, hi.
Okay, in this case, I have a question. We have a prediction coming from massive by gravity theory, according to which gravitational waves from collision of large black holes should be exactly the same as in GR. But for small black holes, there might be deviations from GR, like extra polarizations or something. Can you say something about?
So I'm like, let me go back to here. So it's a little bit kind of difficult to follow. I'm like, here's the evolution of the formed black holes, but you know, we are seeing formed black holes in the 20 to 40 solar mass range, and some of those are strong enough that we can actually use for the tests of general relativity. And at the moment, we're not actually seeing anything coming from those.
But the lightest ones, for example, there is the one with the mass of 5 only, the lightest ones, 5 solar masses. Is there anything special?
So this one here is probably the lightest. I think it's at around 7 solar masses.
Okay, and nothing special.
We haven't seen anything special.
Okay, good.
But you know, before kind of like betting my month's salary on this, I would need to basically look to see if this particular system was used for the general, or for the tests of general relativity. It might have been that this was one of the ones excluded for low signal to noise ratio in spiral or merger or whatever.
Okay.
So if I can ask, what kind of effect would you expect to see?
No, we see that in massive by gravity there are hairy black holes, which are extremely close to Schwarzschild if they are heavy. They're in any way extremely close to Schwarzschild, and the relative difference is something like 10 to the minus negative 34. It's an extremely small number. But this is for unperturbed solutions. When they're perturbed by collisions, so the deviations may show up. And interestingly, there is enhancement of deviation for small black holes. Therefore, if we get gravity waves from collision of small black holes, there might be something there which is not GR. So this is our point.
Okay, that's a very interesting point, actually.
Okay, so
I'll pass it on to my colleagues.
Okay, I will explain this tomorrow in my talk.
Okay.
So please, other questions? Somebody else? Who is there? Cedric?
Yeah. So can I ask one more question? Sorry.
Yeah.
Yes. It's about, in fact, this slide. Ed, can you say a bit about what is the current understanding of the black hole population which is observed by LIGO-Virgo?
Yes and no. So the prediction for the population model has changed. I haven't really been paying enough attention on that particular part of the analysis to say anything kind of beyond that. One of the things that I do know is that our rates predictions are changing all the time.
Okay.
But in terms of the actual astrophysical population, I'm like the paper's out, it's on the archive, but I don't remember the exact conclusion yet.
Okay. Other more questions? If not, Ed, you have done exactly in 40 minutes together with questions. Thank you.